the uniform distribution, and I'm using, and I put a full PDF of this book up and the solutions. So I'm using this, and I really, where's there? Somewhere? I want to say this. I'll be happy to go and use Chan for some of these things, but quite frankly, sometimes he puts enough complications in just the statement of the event, and it really kind of obscures, in my opinion, the essence of what he's trying to get at in terms of the principle. So now we're going to talk about uniform distribution. This is the one, of all of them, this is the easiest. So if you have, I should have done, it's actually, it's a new marker. So when we talk about a uniform distribution, what we're really doing is this. We're saying, if this is f of x, and we have some x1, and this is some x2, the density function will be constant. There will be no variation between these points. So it's just saying between here and here, that's how it's going to look. That's what f of x is going to look like. I'm going to ask you the obvious thing, but I want you to just think about this before you answer. So what would the height of this be, and how do you know? What's the one principle that's overriding? That the integral of f of x dx over the range that it exists has to be 1. Y'all with me on that? I'm just making a point. F of x has to be positive. It can't have negative values, 0 or positive. So if you look at this, it really means if you take the width times the height, it has to be equal to 1. Or this height right here has to be 1 over x2 minus x1. I'm assuming x2 is greater than x1. That's all it is. Now, I think this is evident, right? Now, I'm going to ask you this. Just looking at this, if you ask for the mean value, we'll solve it. But just the mean value of that, what would it be? Well, technically, you would integrate f of x from x1 to x2, right? And if you think about that, it's really taking 1 over x2 minus x1, right? Matter of fact, I might as well do it. I'm trying to make you see the obvious. If we take a look at that, which is the expected value of x, that would be the integral from x1 to x2 of f of x. Well, f of x is just 1 over x2 minus x1 times x dx. Now first, does everybody follow me? It's meant to be just an obvious thing, right? If you look at this, what's it going to be? Well, that's going to be 1 over x2 minus x1, and then you're going to get x squared over 2, so you get a 1/2. Then you have x squared, evaluate the upper one, x2 squared minus x1 squared. First, do you all agree with that? Now, you can factor it if you want, so you have 1/2, and you have x2 minus x1 here. Then up here, this is x2 plus x1 times x2 minus x1. If you factor the x2 squared minus x1 squared, do y'all agree with this? By the way, in real problems with x2 and x1 have actual values, this is obvious and it's easier. But I want to make sure you see this. With me, class? If you take a look at this, you're going to end up getting that. That cancels 1/2, and this is x2 minus x1. So the only thing you do, because it is constant, is figure out what the limits are, add the lower limit plus the upper limit, because it's constant, and divide by 2. Does that make intuitive sense to everybody? Now, if you talk about x squared, the expected value of x squared. By the way, thank you for cleaning it up, because I know some people don't do that. It happens. Of x squared, now you've got the integral from x1 to x2. And it would be 1 over, I'm going to take the f of x out in front, x2 minus x1. And now you're going to get x squared times dx. This is going to be a 1 over x2 minus x1 And here you're gonna get x cubed over 3, or 1/3, and then it's gonna be x3 squared, I'm sorry, x2 squared, minus, not squared, cubed, pardon me, minus x1 cubed. And that would be legitimate. And we can play around factoring that if you want. But honestly, that's just the answer. If you're given specific values of x1 and x2. Y'all follow me, class? That's it in a nutshell. Finally, it's the mean squared value, or sigma of x squared. And that is the expected value of, and here it would be x minus x bar squared as such. The only thing I'm doing is making sure you see the mean value as part of that. Now, if you think about this for a second, we have a probability density function that's constant. And if you look at this, if we just plot x minus x bar versus the limits, I'm going to try to make, this is something I think is important. We take, this is x1 and this is x2. And we're plotting the magnitude of x minus x bar. Just that. You all with me? Well, maybe I'm going to make this a little further away. See, exaggerate something here. This is x2. You can see that what really happens, this is x bar. That's at the middle, right? What happens is you're going to get something like this and something like this. Y'all with me? Everybody with me on this, class? I'm just showing you the function, x minus x bar, not f of x. You're with me in this class? How many understand this? I'm trying to make sure you see this. Now, if you look at this, you know this width right here is x2 minus x1, right? And you know x2 minus x2 plus x1 over 2 is the mean value. The height of this, you can get, and it's really going to be simply, if you think about this, the slope of this line, but you can get this height and this height. Just let me finish my thought. Now that would be for, without putting in the values there, I want you to just get an idea. We can get the values, no problem, but because we'd have to know specific values for x2 and x1 to get the exact value for this. But y'all follow me in this class? Now, if it's an x, if it's this and it's squared right here, then it would look like this. Can you all follow me? And the average value of that, I want you to just see this. I'm getting to a point that where we're going to apply this to quantization error. Have you heard that term, quantization error? Anybody have? Anytime you have an analog signal that can take on all possible values, a sine wave, for instance, and you have a discrete, something where you have to take that and make it discrete levels, where you can go from 0 to 1, or whatever you're closest to, that will be the value. It'll either be a 0, 1, from 1 to 2, and so forth. That's called quantized levels. When you have that, you introduce error, called quantization error. But if you minimize the quantization error, you really don't even know it's there. And you've listened to, I think all of you have listened to digital recordings, right? Of old analog albums. The one thing about that, when you have an analog to digital system that's done right, with the quantization levels, and if the sampling rates suffice twice the highest frequency of interest, there's no noise, there's no hiss. Has anybody heard the long playing albums, the old vinyl records ever? There's one thing you should notice, no matter what they are, you'll hear if you turn up the volume. Hey, do you all know what I'm talking about? It's not there, not at least from the recording, from the digital recording. Sometimes from the amplifier you can get a hiss, but you don't have that with A to D. When you go digital, any kind of digital recordings, the problem with digital recordings is always, and the high fidelity people, they talk about this. Well, no matter how fast you sample the signal, there's still an implicit error that you can't get above. Does everybody know what I'm talking about? With Nyquist, you have to sample twice the highest frequency of interest in order to reproduce it. But with these people that are purists, we need to have an orchestra sound, even though your hearing is from 0 to 20,000 hertz, when the actual sound is produced in the studio, even the higher frequencies, the 40,000, the 80,000, stuff like this, they interact with the environment, and there will be other frequencies that are in the audio range that are created that the digital, if you just capture the sound digitally, you can't recreate that because it's much higher frequency. You with me? So just keep this thing, I'm trying to give you some perspective of things you need to be concerned about with ADD. Anyway, that's what it looks like. Now, I'm saying that for a reason. Now, when we take a look at a analog signal, we make it, we go and, we're going to go ahead and quantize it to levels. And this is done routinely all the time. You've all had, I think you've had to do A to D conversion labs, haven't you? Where you had an analog signal and you had to convert it to a digital, haven't you? Or am I wrong? I might be assuming something that's incorrect.
I think we had done signals. Yeah. One of our signals labs.
You haven't? You should have, and there's two aspects always. It's the number of levels, it's called how many bits you're using, and also the other thing is how fast you're sampling. So I'm only going to talk about quantization right here. When we have an analog signal, we'll use basic sine wave. This is probably the easiest thing to imagine. If you have a sine wave like that, and I'm going to go ahead and say, I want to take that and go from A to D, what you end up doing is saying, and this is in Tom Benny's notes too, but you're going to take this and basically have a sawtooth wave like this that's going to represent the levels. Here would be the max level, then another level right here, another level. It's not very strong, but you can see another level right here. And all these have some, if this is a voltage, a delta V here, and they're going to be n levels. So think about this. We're going to have n levels. I should have done. We'll have n levels. And that means if we have, now, have you heard the term dynamic range? Dynamic range means the total value of the swath in possible voltage, So when you talk about dynamic range, I'm going to have to do something. So I'm going to call this upper level V naught and the lower level here minus V naught. Okay. So the dynamic range would be from the maximum possible positive to the maximum possible negative, it's strictly positive. This is called the dynamic range. Which just means the total, actually, that's incorrect. That's the total range. I'll explain dynamic range in a second. So this is the range that you get. You with me? Now the dynamic range is the smallest possible value of change in a level divided by the maximum possible. So the dynamic range is this. He doesn't really talk about it in his book. Chen may, but I didn't see it. The dynamic range is really equal to the maximum possible value. So it's really the total V magnitude, the extent of V over the magnitude of delta V. And what you can see is, when you talk about dynamic range, typically it's orders and orders of magnitude. Let me give you an idea. A dynamic range on like a voltmeter may be the smallest possible increment, may be maybe 1 millivolt. I'm just gonna use that. So that's the smallest change that it can actually, anything below that, you can't count it. There's too much air. So if we say it's 10 to the minus third, then the maximum possible change in voltage is 1,000,000 volts in this voltmeter. So you have 1,000,000 over 10 to the third, 10 to the minus third, or 10 to the ninth. That's an enormous dynamic range. It's probably an exaggeration. Are you with me on this, class? So that's what the dynamic range tells you, and you always want a very large dynamic range, but whenever you get over about 1,000 or 10,000 for dynamic range, the minute you do that, when you start talking and you're trying to present concepts that people can actually understand, they usually do a logarithm of the dynamic range simply because a logarithm requires orders of magnitude of change for 1 unit change. To go from, if you think about this, log 10 is 1, log base 10, log 100 is 2, log of 1,000 is 3. So you're going up a scale, logarithmic scale, where orders of magnitude are increments. And versus whatever, it makes it a lot more understandable. So remember that. Dynamic range is if it's large, it's very useful to have logarithmic scales. Anyway, with this, what we want to talk about, and this is important, if we say, and the way he does it in the book and other places do, they're going to say, I have something, and I'm going to say that the actual value of the mean is 0. This is simply an example of where I'm going. It'll present the concept without making it too complicated. And I'm going to say if the mean is 0, there's also going to be a dynamic range. By the way, I didn't say this, but whenever they do this quantization bit for any kind of a signal, an analog signal, they assume the probability of the signal being at any point is the same. So it's going to be a uniform distribution. What they're going to have here is something where if the total spread is delta x, the lower value of x1, you might say, would be minus delta x over 2, and the upper point would be delta x over 2, and the actual height of this, the f of x, would be 1 over delta x. I'm going to use this to apply that voltage thing in a second, but I want to make sure I show you this. You all with me, class? Now, based on that, you can see the mean 0. Do you all agree with that? I mean, I stated explicitly, but by one look, if it's symmetric about the axis, about the 0 point, it has to be a 0 mean. Now, what we want to get is the mean squared value. This is something I'm going to work out, and this is very important. You all see if the mean value is 0, then the variance is the same thing as the mean squared value. Do you all with me on this, class? In other words, if x bar equals 0, because if you take a look at this, x squared bar is equal to sigma x squared plus x bar squared. If this is 0, the mean squared value is equal to the variance. Do you all agree? I'm just making a point. So when we do this, what we want to do is calculate the variance. This is what's important with that one. So the variance of that x, and this has to do with quantization, is going to be equal to sigma x squared, but since the mean's 0, it's really going to be the integral from minus delta x over 2 to delta x over 2 of the density function. Well, the density function is just 1 over delta x times x squared. You don't have to subtract the 0 from there. Subtract the mean squared value because it is 0. That's the reason I'm making that point. And then it's dx. Just give me a minute here. Do you all see that, everybody? It may seem like, who cares? Why are you telling me that? You're going to see in a second, this is important. So if we do this integration, we get 1 over delta x, and that would be the quantization level, you might say the total spread. And then when we integrate x squared, we get x cubed over 3, and it's evaluated from minus delta x over 2 to delta x over 2. Can everybody see this, class? Should be obvious. Okay. So, having said that, let's go ahead and evaluate this. This makes sigma x squared equal to 1/3, and then we end up getting 1/3 over delta x, and now we have delta x over 2 squared minus a minus, or it will be plus delta x over 2 squared, or cube, pardon me, not squared, cube. Can everybody follow me on this? If you integrate x squared dx, you get x cubed over 3. You got 1 over delta x is the density function, so you have to have that down. Then you have to evaluate at the limits, right? Because the lower limit is minus delta x over 2, and it would be this minus that, minus 1, you think of it that, to the 3rd power, any odd number is going to be, end up being, you'll change the sign to be a plus. Do y'all agree? Everybody with me on it? All right, so what happens then? I find this is going to be 1/3. Now I got delta x and delta x cubed, so it's going to be delta x squared. And now I have 1/2 cubed, 1/2 cubed. That's going to be 2/8. Y'all agree with that? Just take a look and convince yourself. You with me? What's that going to be? Well, that is going to be delta x squared over 12. This is important. So anytime we have quantization where there's an equal chance of the event being anywhere over, it's basically going to be uniformly distributed. And this is assumed, by the way, for quantization calculation, the error calculations. You get that? Y'all with me? All right, back to this problem that I started to talk about here. And I'll try to be a little more accurate and neat. So if we know that, we know the mean value is 0 for this quantization. Now I'm going to show you what they're really talking about for a lot of this. So here's the kind of deal you get. If you have a signal, and the signal looks like this. It can be time, it doesn't matter what that axis is. This is the signal. Call it voltage. I can say this is V max and this is V min. That means the total spread here, or V magnitude here, or I'll call it V mag. The total change is going to be really, if V min is equal to minus V max here, maybe I'll just use V0 to make it easy. Right here, minus V0. This is going to be 2V0. It's the total spread. And that means delta V, if we have n levels, delta V is just going to be equal to 2V0 over the number of levels. Do y'all follow me, class? Now, if you want to, you can just say this total range, call it V, whatever you want to call it, V max or something like that, it doesn't matter. But if you have that, that means sigma of V squared, or this is the standard, this, I'm sorry, is the variance of that, would be equal to 1/12. And here it's going to be this delta V squared, or 1/12. And here it's going to be 2V0 over n squared. And that would be the mean squared error. Does everybody agree with that? It should be obvious, but I'm making sure. And I'm going to apply it now to an actual exercise in the book, and there's a reason I showed you how it's symmetric about that mean point right there, and this is exercise 2-7.1. I'll give this to somebody. And I want to do this because I think seeing it applied is the most important thing. It'll help you see the reason we're talking about this. Let's see. I don't know. You want to read it? How are you doing? You okay?
Yeah, I'm doing better.
By the way, is Riley here? Is Jared? Yeah. Let me put it over here. You'll need to know that variance and standard deviation for a uniform distribution. So for this one, this is an exercise 2-7.1. Can you just tell me, he gives you a range, a V, right?
Between 0 volts and plus 10 volts.
Okay, that means the total span is 10 volts. Do y'all follow me? If it was minus 10 to 10, it would be 20 volts. Clear, class? Then he says, how many levels? We don't know.
We don't know.
Okay. And what does he want?
How many discrete levels are required for the mean square value of the quantizing error to be 0.01 volts squared?
All right, now, you see the mean squared and the variance are the same. They're, because the mean is 0. Y'all follow me on this, class? It's even though it doesn't look like the mean 0, because we can do this. Does he say mean squared?
Yes.
We can get this first. All right, just follow me. We can get the mean value, and if it's, is it to say it's uniform distribution?
Yes, equal probability.
All right, we can get the mean of that, which is actually gonna be 5 volts for this one, but we can get this. It doesn't matter what the mean is. This will not be affected. Are you with me, class? This will always be correct. So, we're gonna get this first. Are you with me? For this one, we know, and here I'm gonna plot the quantization error from minus delta V over 2 to delta V over 2. And here, we know the height is 1 over delta V. F, it's a density function of V, right there. And that means for this case, sigma V squared is equal to 1/12, and it would be V divided by N squared, and that V is the total span, which is going to be 10 volts. So now I can say this is going to be 1 over 12, 10 over N, right here, squared, is equal to sigma V. And he said that was equal to 10 to the minus 2, isn't that right?
Yes.
Correct, class? So if you look at this, here my sigma V squared is equal to, well, I know it's 10 to the minus 2 here, so let's see. I can go ahead and I have 10, let's get rid of 10 squared over 12 times 10 to the minus 2 right here, multiplied by n squared is equal to n squared. And that means n should be equal to the square root be of 1,000 over 12. I wanna say that's 28 point something, can anybody tell me? I did these problems last time, a bunch of them. I think it's 28.69 or something like that. But the only thing I'm doing, by the way, I'm just solving for n in this equation. So if I multiply both sides by n squared, it gets out of there. Then I have to divide, now I got n squared over there, divide by 10 to the minus 2, and then I have to take the square root.
Sorry, maybe I missed it, but where did 1 over 12 come from? Was that given?
Remember when we did the mean squared value in general in a uniform distribution, we got 1/12,
Oh, yeah,
and it was delta x squared, right?
Mm-hmm.
That was where I got it.
Okay,
And then, that, I'm just applying it now to this problem.
so that's a standard.
That's it,
You can
for
use
uniform.
For uniform, okay.
Always will be, always. All right, so isn't n like 28 point, or what is it?
28.8675.
So technically, n equals 28 point what?
8675.
Now, Elijah, does he have that? It's one of the answers.
Yes, so it says 29 levels you would need.
Yeah, if you wanted n as, that's right, the actual value, you can't have less than that, it has to be greater, so if you're gonna round up, it would be rounded up, and say that, but it would be n equal 29. Now, what's the next part of this one? This is applicable to what happens in the real world, by the way. Go ahead.
If the number of discrete levels is to be a power of 2 in order to efficiently encode the levels into a binary number, how many levels are required to keep the mean square value of the error not greater than that 0.01?
All right, first, you've all heard the terms like 12-bit, right? 12-bit, 10-bit, stuff like this. What does it actually mean? If you have any number of, like if you have 12-bit, you're gonna have 12 spaces. This first is gonna be ones, the second is gonna be twos, right? Then 4, then 8. Each one of these things is going to, the number of 8s and stuff is going to be 2 to the nth power, where n is an integer value. Are you with me on this, class? So if you talk about something where you're going to have 29 levels, well, that doesn't work in terms of if we want to take that and put it into a binary number. So they always will try to get n to be something where it's a power of 2. In other words, 2 to the 0, right, would be 1. 2 to the 1, 2 to the squared is 4s, and so forth. You all with me? So you can take any large number, any large number, and you can go ahead and turn it into a binary number. And I think you've had to do that in your classes. I don't remember which one, but computer science, what was the class?
Digital logic.
Digital logic, did you all have that? All right, so this is the type of thing that is normal. So for this one, if you look at this, n is 29, we have to be 29 or greater. Well, if you take 2 to the, 4 to the 16, you with me on this? 2 to the 5th would be 32, do you agree? So there has to be 32 bits. So n would be 32, that would be the next possible value if you're using 2 to the n as the value. You all with me, class? It would be 32, and for this, it would be what? I'll call it small n equal 5. Do you agree? So it would be 5-bit. You think about this, correct? Just a minimum value. Could be much higher than that. Okay, if we have that, what else is that right? I think it is.
Yes.
What else is good?
If the number of if 32 levels are used, what's the actual mean square quantizing error?
All right, now we go back to the original calculation. We want sigma of this, we might call it delta V. I'll just call it sigma of V squared. Well, we know that's equal to 1 over 12, and now we have to take the total range of 10 divided by 32 squared to get that. With me? Because n now is going to be 2 to the 5th or 32. Does everybody follow the logic in this one, class? Are you with me? Okay. I don't know what that is, but you you can do it, so it's really what, 100 over 12, and then you get 32 squared. I can mess around with this, but why don't you just tell me, because I don't know.
I've got, 0.00814.
Is that the answer? I think they have 3.0.
They were 0.003, but then there's another written that was 0.008.
It should be 0.008. I
Yeah.
think that's just a typo in the book. I think it should have been an 8, but they put a 3. I mean, in the actual answers he has stated, and you have access to this in that text. What page is that on, by the way?
91.
All right, just write down page 90 for us. You good with that, class? And in a nutshell, I want to tell you this. The really important thing, in my opinion, for this kind of, for a uniform probability density function, we could always, I could take problems like this, can ask for the fourth, I could ask for the fourth central moment. What's the fourth central moment? It'd be 1 times 3 times what? Sigma v to the 4th power, right? It's basically, you can manipulate that. Any odd values, if I ask, because it is symmetric, it's uniform. If I ask for the, now this is true for Gaussian as well as uniform, what would the 3rd central moment be?
0.
The 5th central moment?
0.
Okay, everybody understands the idea behind that. And it's true for Gaussian and for this, all right, because that's symmetric about the mean value, which is 0. Okay, next, we're going to go to something that's useful. This is the last distribution I'm going to actually cover. And this is something where it's an exponential distribution, but it deals with the mean time to failure of an event. And this is an important one too, because it actually, this is something, this distribution is a very accurate representation of the probability density function for a lot of events in the real world, like failure, time to failure of, say, vacuum tubes, time to failure of a lot of things that are electronics, especially with heating involved. A vacuum tube has to have a hot filament. I don't know if you know that or not. Did you have any theory about vacuum tubes? All right, well, at one time, they did this because vacuum tubes were used instead of transistors, but a vacuum tube is something, and you should at least have some history. Nobody's told about this. They basically have a glass chamber like this, and there's a vacuum in there. Now, it's not a perfect vacuum, it's very, very low pressure. And the glass is thick, and they have something called a filament. And that filament is going to get very hot. Now, when you have, and it's metal, when metal is heated up, it allows electrons to be emitted with almost, there's very little surface energy needed for it to actually get out. And when you have a vacuum there, it's much easier. And then these things will have, this is called cathode. This is true for so many things, by the way. You know what scanning electron microscopes are? Have you heard of that? Scanning electron microscopy. It's basically, you get something where you have a very low vacuum and you put a target in there and you have to put a conductive coating. Typically it's either a gold film or something like that over it. And then they have a filament up here and they heat it up. And then they have grids that accelerate the particles, basically a voltage difference. So they'll have grids. And like a triode will have 3 grids, a pentode 5, but they'll have these electronic grids as such, and they show them dashed line like that, and they put a voltage difference here. So the electrons coming off get accelerated there, and here's the thing. Some of them do hit the grid and are pulled out, but a lot of them get right through the spacing in between. They're spaced in a way, if you think about this, if you have negative and negative potential, positive and positive potential, and this electron's gonna come zooming up here really fast. It's right dead center. It doesn't turn that way or that way, it goes right through that grid. This is the way it works. Now, they're set up in a way so the acceleration from here to here to here to here, it keeps on getting more and more. And by the time it gets past this, it's got very, very little. I mean, if it was allowed to go on forever, it'd come back down and hit here. But then they have an anode up here that'll catch that. Now, the idea is this, they put a voltage difference on here that might be like a small sine wave. And what that means is the current through here will vary as the sine wave and hit to here, but it will be amplified. It'll be a much more current, much more voltage, so they can take that and use it. Now, you know, a bipolar junction transistor is what? A voltage control current device, right? Isn't that right? Where a small voltage controls a large current in the output circuit. Do you remember this? How many have had BJTs, bipolar junction transistors? And it's the same for MOSFET. Small voltage controls a large current. These are voltage controlled voltage magnifiers, or basically amplifiers. So it is different, slightly different. But it does, these voltages from here to here are massive compared with the grid voltage. And it works flawlessly. As a matter of fact, one other thing I might as well say, because I'm trying to give you a little bit of history you should know if you get out of an engineering program. Something else you should know about this, these things are immune to EMP from like a nuclear weapon. Now, anytime you're dealing with failure of device, transistors, what you're talking about is the atomic structure, the crystalline structure gets ruptured or broken down because of a very high energy electromagnetic field that hits them, disrupts them, causes shorting, and they're not self-healing. These have no problem. As a matter of fact, this is a story from like 20 years ago, and it's true to this day from everything I know. We spent a lot of money hardening or preventing our electronics and our planes and stuff from failing if a nuclear weapon went off near them. The Russians just use vacuum tubes. And they have a lot of people say, well, vacuum tubes are big and you know, quite frankly, they're old school. I mean, who needs them? It's like using a slide rule and you got a calculator. But the thing about vacuum tubes that people don't appreciate is in World War II, we had vacuum tubes that looked about the size of my pinky, like that, super small. And those things could survive the acceleration being shot out of a cannon. You know, one of the things people think about, you know, you kick this thing real hard, a normal size vacuum tube, and this will break and it won't work. Well, they figured a way to scale them down. They're so small and this stuff is so rigid. You could shoot them out of a cannon and they would still function. Now, why is that important? Well, because the first type of anti-aircraft artillery that was used had proximity type fuses where they'd find a magnetic signature that got close enough to the plane, or it used a radar, and anytime there was a reflection that was sizable, they'd blow up. That was the very first AAA fire, or basically anti-aircraft artillery, and it used vacuum tubes. To this day, vacuum tubes are very important, as far as I know, for a lot of things that have to be invulnerable to electromagnetic pulse from a weapon or from any kind of an event. Are you familiar with EMP, that term, at all? I don't know where people, you probably got it just from, I don't know, watching movies or something, but it's a very deadly thing. And one last thing I'll say, you should have this history. Long ago, when the first nuclear weapons tests happened, there was a test that we did, and it was in the Bikini Islands. Has anybody heard about this? There was starfish and fishbowl, I think were the two. What they did is lit off a huge hydrogen bomb about 2,000 miles from Hawaii. So it was an airburst. This is not underwater. This is a massive amount explosive. So the thing went off, and the entire power grid in Hawaii went off. As a matter of fact, they couldn't communicate with the ships. So the picture, of course, that people had is we killed everybody. I mean, basically it went off. Somebody didn't do the math right, and it was so big it killed all the people on the ships watching, took down Hawaii's power grid. Now they did a very good, there's a guy named Conrad Longmire. I know about this because of my doctor. Conrad Longmire was doing a lot of stuff, I believe at that time. And everybody was focused on the fast, the EMP that would destroy electronics. What they didn't realize is when a nuclear weapon went off, there's a massive amount of positive charge. It's called a positive fireball left. And I don't know the amount of charge, but ridiculous. Probably millions or hundreds of thousands to millions of coulombs. This is ridiculous. Typically, lightning has charge centers where charge displacement is of the order of maybe a couple ohms, and you get a peak current of about 20 kiloamps. This thing is so many orders of magnitude larger, it's ridiculous. And what happened is all the electrons from a nuclear blast get scattered all over the place. These are electrons, they're called Compton electrons. Have you heard that term, Compton electrons, from physics? He has, but if you have modern physics, you have. If you haven't, you probably just picked it up somewhere. Anyway, these things get scattered all over the ionosphere, but all that charge wants to get back to its parent charge, which happens to be a hot, very positive nuclear center. So how does it get back to it? Think about just basic electrostatics. Well, it finds the path of least resistance, right? The power grid on Hawaii, by the way, water is a great conductor, the surface of water. So it goes along the ocean surface, and when it gets to Hawaii, it goes right through the power grid. And you know how they have fail-safe transformers and stuff like this? I don't know what they had there at that time, but it took out everything. So the whole power grid's gone. And when they figured out what happened, that was my doctoral work, by the way. It was all on late time electromagnetic field signatures and reconfiguration from charge perturbations related to lightning, which is a lie, which is related to this time. Anyway, that thing changed a whole lot of people's ideas about how to deal with nuclear weapons. That's still a big problem that they don't talk about very often. It's always the very high frequency stuff, but something for you to know in the real world. I've got a lot of stories about this I found out about later. Those currents are so massive, by the way, from some of that. You know, the desert was the first nuclear weapons test out in Nevada and stuff. Are you familiar with this? These are atomic bombs, they're not hydrogen. Well, out west, there's a whole lot of railroad tracks. They're buried and stuff, mines, you know. Railroad tracks are very good conductors. So this is a story I was told. I've never seen it in the literature. And if it is in the literature, it's probably taken out by now. But they found railroad tracks. You all know the current in the same direction pulls together. You familiar with that from ELEC? Right, they found pieces of railroad tracks, I guess, under earth that were pulled together because the current was so massive it could generate that amount of force. They figured this out. This current is ridiculous. It's like 10 hundreds of millions of amps to do that. And it has to be sustained, which gave people an idea we have a bigger problem than we thought when we light one of these things off. Just something for perspective on that, about this. Anyway, I had to tell you about vacuum tubes. I needed to work that in. It seems logical. Okay. Now we're going to talk about the mean time to failure. And this is a very good representation of failure on anything with a heated cathode, as well as a lot of other things. Now, in his book, or in his discussions, it's called the exponential distribution. So what they do is say there's going to be something, and I'm going to call it of tau, of t, and it has a value of 1 over tau bar, and tau bar is called the mean time to failure. What that means, on average, it takes this long for the thing to fail. 50% of the time it fails less, 50% of the time it'll fail at a greater time. Y'all with me? They're just using tau bars for that. And then it would be EXP, I'll use tau here as a symbol for time, of tau minus tau over tau bar. So that's the mean time to failure. Can everybody follow me on this? Now the first thing you have to do is make sure, if you look at this, this is what the density function looks like for this. Ooh, something I didn't say. If you have any event and there's a failure, and you want the probability it fails again, it will be exponential from that point on. Do y'all follow me on that, class? So suppose something can fail at any time, but it's self-healing. Now, are you familiar with capacitors that are oil-filled in here or not? There are capacitors that are called self-healing. This is the best example I can think of. They're filled with oil. So if there is an arc over, unless they blow up, It's self-healing. When the arc stops, it's liquid oil and it's still an insulator. It's called self-healing. So if there's some kind of a random signal, and this thing fails at a given point, if it has an exponential distribution mean time to failure, the next failure will have that statistical information. You with me? This is what he talks about. So if you look at this, that means the probability of a failure, and I'll just call it FA, failure, less than or equal to some time t would be equal to, now that's the probability of a failure, right? So it'd be the integral from 0 to t of this function, which is 1 over tau bar exp to the minus tau over tau bar d tau. The only thing I'm trying to do is show you, I'm integrating that just like you would any density function. So this is the probability a failure happens at a time t. Well, if you integrate this thing, you're going to get a value of basically e to the minus tau over t bar right here, evaluated from 0 to t. And here, there's a minus sign. Well, you could switch the limits and you end up getting 1 minus exp to the minus t over the mean time to failure. Can you all follow me? Now that's the probability that it fails at an interval from 0 to t. And if you look at that, it has to, if you go to infinity, this has to go to 1, and in fact it does. That's the mean time to failure. The probability it doesn't fail would be this, right? And it would actually be 1 minus this, correct? Or the probability this doesn't fail, or the failure is at less than t, the probability that it doesn't fail up to t would be equal to simply e to the minus t over tau bar. And you can see the probability it doesn't fail, this is supposed to be the mean time of failure. The probability it doesn't fail asymptotically goes to 0 as t goes to infinity. Can you all see that, Cliss? So this is kind of an interesting distribution, but here's what it also means. If you have some kind of event, you know it's the statistical information, the probability of failure is going down. But then if right here there's a failure, what happens from that point onward, you get another statistical distribution. Can you all follow me in this class? So it's important to appreciate this. The failure of a device, if it has failed before, or it may fail 20 times before, has nothing to do with the statistic. It fails after the last failure. And this is real important. So the mean value of this thing is tau, and in the book he's going to say what the mean squared value is too. And, oh, the variance, I didn't put this down here. So for this one, when we talk about this, the mean time, or the expected value of time to failure, this tau bar, and the expected value, and this would be called the variance, actually. The variance of the time to failure is going to be equal to tau bar squared. You can prove that if you want, but it's pretty straightforward, which is interesting, because tau bar and the variance and the mean value are related just by the square of one to the other, or the square root. Okay, so I'll ask you a question about this that would be legit. I'm going to do it on this board. have, I think this is something we're talking about spacecraft in the one, the first example. Anyway, the mean time to failure is going to be 100 days. That's called just the mean time to failure. And they say, what is the probability of not failing for 200 days? So they want the probability of not failing for 200 days. Now just think about this logically. You know that this is the density function for failure, right? You with me on this? So the probability it goes up to a certain point, there's a failure between here and here. That probability, or the f of t, is equal to 1 minus exp to the minus t over tau bar. Can everybody follow me on that? That's of it failing somewhere between the interval of 0 to the point t, right? What's the probability it doesn't fail?
1 minus.
That's it. Or, that's right, the probability it doesn't fail, not failing for 200 days, is 1 minus exp minus 200 over 100. So that's the probability of it failing. And then I have to take 1 minus that. And you can, I think just looking at this, you see it. That means it's going to be simply exp to the minus 2. And in fact, that's right, I don't know what the value is, but it's 0.1325. I think you guys appreciate this. And then I'll give you this one. So they got an example, t equals, or the mean time to failure is 4 years. Now, I tell you, I don't need to do that one. The next thing I want to talk about is a delta distribution for a reason, because a delta distribution is something where you're going to have discrete possibilities. Say you have 2 levels of a system, a 1 and a 0, or a minus 1 and a 1, right? Then the probability of a 1 could be P1 delta of, call it x minus 1, plus probability of the other one, which is 1 minus the probability of the first event, times delta of x plus 1. That would be a delta function distribution. Are you with me? I want to just cover this because I need to for a reason. Because it does have to do with typical types of things in digital processing. By the way, does this one seem pretty obvious to you? Mean time to failure? To me, it seems very obvious. We'll get into how you can make this a little more complex after I talk about conditional probability. All right, this is called a delta distribution. And the only thing they're talking about is they're going to have, I'm going to use this, f of x, this is a density function, some p1 delta of x minus x1 plus p2 times delta of x minus x2. Now, there could be more, but the most common example used are going to be things where there's just, it's binary, 2 possible states. If you think about this, just tell me your gut on this one. What would be the expected value of x for this one? Well, instead of an integration, we have a summation, right? So technically it'd be the summation of x of I, here I would be equal to 1 and 2, of that value times the probability of x of I. Well, that's really going to be P1 times delta of x minus xi plus, I mean, that's basically it. And if you think about this, it's really just going to be what? P1 times x1 plus P2 times x2 if you have only two possible states. Do y'all follow me? By the way, what is P2? 1 minus P1. Do you agree? If that's only possible values, probably. So that's it. And I can say this too. What would the expected value of x squared be? Now just think about this. So it would be the probability of the first event, right? P1 times x1 squared plus the probability of the second event times x2 squared. Does that make sense? It's just, instead of an integration, it's a summation, only two terms. It's always going to be x to that power squared in this case. It would be the mean squared value. When we take a look at the standard deviation, or sorry, the variance of this, now if you've got that and you've got that, and you go ahead and you say if I take this minus this squared, what ends up after you manipulate it, I'm just going to write it down. It's going to be P1, P2. By the way, in the real world, if I gave you a problem, you would have probability like x1, 0.5, value of x1, 1. Probability of x2, 0.5, value of x2, minus 1. Follow me? This is a no-brainer. That would be 0 for that. Over here, because you have the p and value of x, it's a no-brainer too. Y'all follow me? And for you to get the next part, 6 squared, you would take that square, this minus that squared. And those things are easy to do with real numbers. That I promise you. Factoring gets a little tricky, but this is what it does come down to. P1, P2, and here it's going to be x2 minus x1 squared. That's what it will be for any general value. And I'm going to skip. I was going to do this with coin toss number of heads, but I'm going to skip that. It's a very obvious one if you've got this information. I say the event is number of heads in tossing a fair coin 3 times. Well, the probability of no heads, you don't care about, right? Probability of 1 head, if you think about that binomial distribution, it would be n or 3 cubed over, 3 factorial over 1 factorial, 2 factorial. Really, it's going to be 3. And then, because it's a fair coin, the probability to the k times 1 minus the probability of that to the n minus k is really just going to be a factor of 1/2 to the third. So I'm not going to bother too much on that one. But it really isn't bad to do that problem. I'll put it up as a homework, all right? But I want to cut to the chase on something else. In the last 10 minutes, I want to talk about something where we have conditional probability, or the probability of event A given event B occurred. But we're really going to be talking about event B directly related to the statistics of event A. And I have to show you this. Just about done with this chapter. And we're going to get into some things that get more complicated in a hurry. So, I'm trying to think of terminology he uses for this, but and with radar, at least there is a direct application of this. A lot of stuff I have done. And here's, in general, when they talk about conditional probability, symbol they use is, like, they want the cumulative density function of X given event M had occurred. So I'm gonna try to show you kind of a picture of how this works. If you think about the density function f of x, I'm gonna do one like this. Let's say it's just a Gaussian like this. Something like that. With me? And then we say that an event has occurred, or that x has to be greater than or equal to m. So if I say that this occurs, basically what I'm saying, this has occurred, or somewhere between here and here the event has happened. Does that make sense? If I say it has occurred, now this would be like the event M has occurred. We don't know. We know the statistics, we know the probability density function, but now we want the probability given that this has occurred. And by the way, we're just saying that the range now has been reduced from minus infinity to m. Now they want the statistics of the new density function, and that would be f of x given m has occurred. Y'all follow me on this? Just try to appreciate this. Now we're saying the range is limited. Before it went from minus infinity to infinity. Y'all follow me? Now it says the range of f of x given m is from minus infinity to m. It's no longer possible to be greater than that. So we know one thing, that if I take the integral of f of x given m has occurred dx, and I integrate from minus infinity to m, it has to be 1. You all follow? If m has occurred, and you know, don't worry too much about how this can be defined. If we say your car can't go more than 80 miles an hour, then what's the probability it's going 30 miles an hour? You all follow me? You've limited the range, even though maybe in general speedometers can go, I don't know. I've never seen one over 150 miles an hour, but I'm sure there are kinds like that. So now you've limited the range. When you do that, because of this, what really happens, and I'm just going to make it clear, what you really do is, if I want the statistics for f of x given m, it's really just taking f of x, the original value, and dividing it by the area from minus infinity to m of f of x dx. What it really amounts to is now we're normalizing everything. Now think about that. That area right there is the area from here to here, right? And if I take the actual f of x right there and then divide it by that area, when you integrate that out, because we've scaled it by the area, it will be 1 when you do the integration. Can you all see this, class? Just take a moment and try to appreciate this. This is the only thing you're doing with this type of conditional probability. And in the book, well, I haven't looked at Chan's on this one, but it isn't hard. It really isn't. So, let me say one other thing about this. I struggle sometimes to think of very good ways of coming up with problems where this applies. The book is much better at finding ones. This type of a problem is perfect. We're going to, he has, I don't know what example this is. Oh, it's exercise 2-8.1. Can you take a look at that? Let me finish this and I'll let you guys go, but I want to make sure I get through this part, because the conditional probability stuff, the first question is, well, how do I know the probability of the second event has anything to do with the probability of the first event? It's implied. That's the thing. He's saying the statistics have to do only with one distribution function. I didn't say that clear, but that's implied. Okay, now I'll try to draw this. Here's the deal with this. He's going to say he has a voltage source. This one's going to require some knowledge of the Rayleigh distribution. It's gonna say this voltage source here is Gaussian. So F of V is gonna have 1 over the square root of 2 pi sigma V, EXP, it's gonna be a zero mean though, so zero mean of minus V squared over 2 sigma V squared. That's the statistics of this voltage. But then he does something that he doesn't usually do. Now he's gonna put a diode there. What a diode does is rectify the current. It only allows the current in one direction. Do you follow me? And then he's gonna have a resistor. I think the value, tell me if I'm wrong here, but I think sigma of V is 100 volts, is that right?
Yes,
And I think R is 50 ohms.
that's right.
All right, I like this problem because this is the kind of problem I could see on like an FE exam. Or if you go for a job, I mean, I can't predict what they'd ask you, but depends what guys are probably good at that interview. But I can see this happening. So this is 50 ohms, and they have current here, I. So what their question is, what is, I think it's the mean value of I, isn't that it? So it wants the average value of I. Now, the way I've drawn this diode, current can only flow this way, right? I want to make sure everybody sees this. You all with me? That's what a diode does. We know this voltage can have values plus or minus. So if you look at the possible voltage values here, you're going to have negative values here, positive values here. Here's the density function, right? Everybody with me on that? Y'all with me? I'm just showing you the density function. It's Gaussian. But the current can only have values that's positive with that diode, the way I've drawn it. So we know the current can only have values that are positive. And that means I'll call it the F of I, because it's only positive. What we'd like to do is first say what I is. I itself is equal to V, right, over R, correct? But now, what we'd like to do to get this average value, or the expected value, that would be 1 over R, but it would be the expected value, right? Assuming V is positive. Let me just show you how we do this. So now I have to take a look at the statistics of the density function for V, right? What we're going to do is, what I'm going to do here is, I'm going to calculate the expected value of I, so I got 1 over R here. Now I have to multiply that by V, because it's an expected value, V. Now it's times F of V, right? And F of V here is the Gaussian, which is 1 over the square root of 2 pi sigma V. And it would be times EXP, right, to the minus V squared over 2 sigma V squared. Remember, this is the statistics that I'm using as the Gaussian statistics from the voltage, which basically has possibilities of positive and negative. But now I just need of the positive values here, it's dV. Because the negative values they do not contribute to this value. And it would be from 0 to infinity. First, convince yourself of this. If it's a Gaussian distribution for V, right? The only part of that Gaussian distribution that's going to affect I is the positive values from 0 on up. You all with me, class? So now I take that, which is this exponential, and I have to multiply it by V because I need the mean value of that voltage, right? And then I would get this. Now take a look at what this is actually going to be. And I'm going to break out some stuff here. So I'm going to take 1 over R, and then I'm going to divide that by the square root of 2 2 pi. Here's where I'm going. I know what the distribution, that if I integrate from 0 to infinity of r, well, I'll put capital R here, over sigma squared exp to the minus r squared over 2 sigma squared dr, that's a Rayleigh distribution. For that Rayleigh distribution, square root of pi over 2 times sigma. And you may not remember this. If you didn't do the problems, you'll start doing the problems, I think, after that. I'm trying to figure out. I don't know what page this is on, but it's in the book. So this would be, if I look at just this integral, this is really the expected value of r, or r bar for the Rayleigh. Do you remember Rayleigh distribution class? It was the one where you're shooting arrows at the target, bullseye, right? If you have that, now look, see that? I'm showing you the integration. Your calculator will do this integral. So you wouldn't even have to worry about this whole thing. So I have r here is going to be the resistance. And I have over square root of 2 pi. Now look, see how I have a sigma v there, but I have to get a sigma squared there? You all see that? That's sigma squared I need there. So look, and that r would be akin to v. Now I take v, and I have over sigma squared, and I have to multiply this by sigma. Just bear with me on this one. And it's going to go from 0 to infinity, and now it would be exp to the minus v squared over 2 sigma squared dv. What I'm really trying to show you is capture the fact that r is just like this. That r right there is resistance. That r is like the Rayleigh r. Sigma squared is here. That r is like the v. That sigma is here. And that whole thing, right? This integral goes to square root of pi over 2 times sigma. So this whole thing, I want this stuff out in front, I broke out for a reason. So I take sigma over the resistance. Is the resistance 50 ohms? Yeah, it is. Over 50 times square root of 2 pi. And then this integration becomes square root of pi over 2 times sigma. Let me finish this, I'm sorry, it's taking so long. So I can say I got a sigma squared, and then the pi's cancel, and I get square root of 2 square root of 2, so it's over 2, and then I get 50. Or the expected value of I here should be, what was sigma again? Sigma?
100.
So it's going to be 100 squared. So it's 100 squared over I think I made a mistake here. Hold on for a second. I did. And this breakdown right here, sorry about this. It has to be times 2 right there. This isn't gonna make a whole lot of sense to you. I'll have to talk about this last part, but when you do the statistics, if you just do this integration right here, with the right statistics, you're gonna end up getting this equal to 200 over the square root of 2 pi divided by 50. And that should be 1.596. I did this last time. I failed to say something. This information, statistical information for that voltage, because it's, we're only taking the positive statistics, this has to be multiplied by 2, and I know I'm holding it. I'll finish up that thought next time, okay? And I'll give you some homework, but I wanna go through this. That is exercise